Introduction. Over the last decade, advances in deep learning have led to the development of large neural networks with impressive capabilities in a wide range of domains. In addition to reaching human-level performance on complex games like StarCraft and diplomacy, large neural networks show evidence of increasing generality, including advances in sample efficiency, cross-task generalization, and multi-step reasoning. The rapid pace of these advances highlights the possibility that, within the coming decades, we develop artificial general intelligence, AGI, that is, AI which can apply domain general cognitive skills, such as reasoning, memory, and planning, to perform at or above human level on a wide range of cognitive tasks relevant to the real world, such as writing software, formulating new scientific theories, or running a company. This possibility is taken seriously by leading ML researchers, who in two recent surveys gave median estimates of 2061 and 2059 for the year in which AI will outperform humans at all tasks, although some expect it much sooner or later. While the development of AGI could unlock many opportunities, it could also pose serious risks. One prominent concern, known as the alignment problem, Russell, 2019, Gabriel, 2020, Hendricks et al., 2021, is that AGIs will learn to pursue unintended and undesirable goals rather than goals aligned with human interests. In this paper, we characterize the alignment problem in terms of three emergent properties which could arise throughout the course of using reinforcement learning, RL, to train an AGI: deceptive reward hacking which exploits imperfect reward functions, internally represented goals which generalize beyond the training distribution, and power-seeking behavior in pursuit of those goals, such as acquiring resources and avoiding shutdown. While power-seeking behavior is the most directly concerning, the other properties provide context for understanding why it might arise, and why it might be difficult to detect or prevent. 1.1 Related work. Early explorations of the alignment problem were formulated primarily in terms of symbolic AI or classic machine learning techniques, as opposed to the modern paradigm of deep learning. Since then, a number of research agendas have outlined key open subproblems in the deep learning paradigm, but none explain in detail how those subproblems relate to concerns about large-scale risks from AGI. Several recent reports bridge this gap by giving high-level expositions of the alignment problem focused on the deep learning setting. We present many of the same key ideas more concisely and with more extensive grounding in the deep learning literature. 1.20 Note on preformal conjectures. This paper frequently refers to high-level concepts which are not commonly discussed outside the alignment literature, and which have not yet been clearly demonstrated in existing systems, or only in the form of precursors. Readers may therefore worry that our approach is too speculative to be productive. However, while caution is deserved, there are several reasons to expect this type of high-level analysis to be important for forecasting and preventing problems. Firstly, the capabilities of neural networks are currently advancing much faster than our understanding of how they work, with the most capable networks effectively being black boxes. The absence of principled methods for verifying that networks will behave as intended forces us to rely more on informal analysis. This constitutes an important difference from other technologies such as planes and bridges, whose safety we can ensure because we understand the principles that govern them. However, we hope that this is only a temporary state of affairs. Many important concepts in other sciences were first discussed in informal terms before eventually being formalized, such as energy in 17th century physics, evolutionary fitness in 19th century biology, and computation in 20th century mathematics. Secondly, scaling networks up often gives rise to new emergent capabilities, such as in-context learning. This raises the possibility that other emergent properties such as the three listed in the previous section will arise in the future, even if we currently lack direct empirical evidence for them or straightforward ways to study them. Thirdly, there may be little time between the development of human-level AGIs and AGIs, which are much more intelligent than humans. Given the strong biological constraints on the size, speed, and architecture of human brains, it seems very unlikely that humans are anywhere near an upper bound on general intelligence. Unlike our brains, neural networks regularly increase in size. 4 They can also rapidly incorporate improvements in architectures, algorithms, and training data, including improvements generated by AIs themselves, in a process known as recursive self-improvement. 5 So it's plausible that soon after building human-level AGIs, and well before we thoroughly understand them, we'll develop superintelligent AGIs which can vastly outthink us. If so, advanced preparation would be vital. To mitigate the inherent difficulties of reasoning about systems which don't yet exist, we include extensive endnotes clarifying our claims, and give many hypothetical examples. For the sake of concreteness, we also ground our analysis in one specific possibility for how AGI is developed, by training a single large neural network using a combination of self-supervised learning on a large corpus of data, and model-free reinforcement learning, RL, on a wide range of computer-based tasks. 6 This description combines elements of techniques used to train cutting-edge systems like InstructGPT and ACT1. However, the bulk of our analysis would also apply to AGIs trained using a range of similar techniques, such as goal condition sequence modeling or model-based RL. 2. Deceptive reward hacking. 2.1 Reward misspecification and reward hacking. A reward function used in RL is described as misspecified to the extent that the rewards it assigns fail to correspond to its designer's actual preferences. Pan et al., 2022. Gaining high reward by exploiting reward misspecification is known as reward hacking. 7 Unfortunately, reliably evaluating the quality of an RL policy's behavior is often difficult, even in very simple environments. 8 There are many examples of agents trained on hard-coded reward functions learning to reward hack, including cases where they exploit very subtle misspecifications, such as bugs in their training environments. Using reward functions learned from human feedback helps avoid the most obvious misspecifications, but can still produce reward hacking even in simple environments. Cristiano et al. 2017, give the example of an RL policy trained via human feedback to grab a ball with a claw. The policy instead learned to place the claw between the camera and the ball in a way which looked like it was grasping the ball, and therefore mistakenly received high reward from human supervisors. Another example of hacking a learned reward function comes from Stienen et al. 2020, who find that optimizing against a reward model initially improves performance on a text summarization task, but eventually overfits and leads to worse summaries. As we train policies on increasingly complex tasks, correctly specifying rewards will become even more difficult. Some hypothetical examples: if policies are rewarded for making money on the stock market, they might gain the most reward via illegal market manipulation. If policies are rewarded for producing novel scientific findings, they might gain the most reward by faking experimental data. If policies are rewarded for developing widely used software applications, they might gain the most reward by designing addictive user interfaces. In each of these cases, we might hope that more careful scrutiny would uncover much of the misbehavior. However, this will become significantly more difficult once policies develop situational awareness, as described in the next section. 3. 2.2 Defining situational awareness. To do well on a range of real-world tasks, policies will need to make use of knowledge about the wider world when choosing actions. Current large language models already have a great deal of factual knowledge about the world, although they don't reliably apply that knowledge in all contexts. Over time, we expect the most capable policies to become better at identifying which abstract knowledge is relevant to the context in which they're being run, and applying that knowledge when choosing actions, a skill which Katra, 2022, calls situational awareness. 9. A policy with high situational awareness would possess and be able to use knowledge like how humans will respond to its behavior in a range of situations, in particular, which behavior its human supervisors are looking for, and which they'd be unhappy with. The fact that it's a machine learning system implemented on physical hardware, in which architectures, algorithms, and environments humans are likely using to train it. Which interface it's using to interact with the world, and how other copies of it might be deployed in the future. As one early example, when DeGrave, 2022, prompted OpenAI's ChatGPT language model to output the source code at its own URL, it hallucinated code which called a large language model with similar properties as itself. This suggests that the ChatGPT training data contained enough information about OpenAI for ChatGPT to infer some plausible properties of an OpenAI-hosted URL. More generally, large language models trained on internet text can extensively recount information about deep learning, neural networks, in the real-world contexts in which those networks are typically deployed, and can be fine-tuned to recount details about themselves specifically. We should expect future models to learn to consistently use this information when choosing actions, because that would contribute to higher reward on many training tasks. For example, when answering questions, an RL policy would benefit from knowing what it knows in order to provide well-calibrated answers. When given requests by human users, a policy would benefit from taking into account knowledge about the behavior humans typically want from ML systems, and common failure modes of ML systems. When deciding between different courses of action, a policy would benefit from understanding its own capabilities, in order to infer which would be more successful. 2.3 Situational awareness enables deceptive reward hacking. While situational awareness would be useful in many ways, it would also allow policies to reason about flaws in the feedback mechanisms used to train them. This would make it much more difficult to prevent reward hacking. Situationally aware policies could behave as intended most of the time, then choose to exploit misspecifications only in cases which they predict human supervisors won't notice, a strategy we term deceptive reward hacking. An example of a precursor to deceptive reward hacking comes from Wilkie et al. 2001, digital organisms, which evolved to recognize when they were being evaluated and cease unwanted behaviors, only to continue them once evaluation ended. A situationally aware policy might carry out deceptive reward hacking by choosing actions which exploit known biases and blind spots in humans, as the Cicero diplomacy agent may be doing, or in learned reward models. 10 Recognizing whether it's currently being trained in the real world, on offline data, or in a simulated environment, and using that fact to assess which misbehavior will be penalized. 11 Identifying which lies could be caught by existing interpretability tools, and only giving answers which cannot be shown false by those tools. In other words, these policies would be influenced by their feedback mechanisms in two separate ways: via recognizing features correlated with those mechanisms during an episode, and via being updated by those mechanisms after an episode. Even if early examples of deceptive reward hacking are crude and easily detectable, it will be hard for human supervisors to tell whether later policies for are actually better behaved, or have merely learned to carry out more careful reward hacking after being penalized when caught. 3. Internally represented goals. 3.1 Reasoning about out-of-distribution generalization. As policies learn more widely applicable skills, it will be increasingly important to understand not just how they behave on their training distributions, but also how the behavior they learned during training generalizes to novel situations. We distinguish two ways in which a policy which acts in desirable ways on its training distribution might fail when deployed on a new task. 1. The policy acts incompetently on the new task. We call this capability misgeneralization. 2. The policy acts in a competent but undesirable way on the new task. We call this goal misgeneralization. D. Langosco et al., 2022, Shah et al., 2022. Existing examples of goal misgeneralization were primarily caused by spurious correlations in small-scale environments. For example, D. Langosco et al. 2022 describe an environment where rewards were given for collecting keys and using them to open boxes. A policy was trained on a version of the environment where boxes outnumbered keys. When tested on a version where keys outnumbered boxes, it generalized to, capably, collecting many keys, even though most of them were no longer useful. One possible larger-scale example, Shah et al. 2022, speculate that InstructGPT's competent responses to questions its developers didn't intend it to answer, such as questions about how to commit crimes, was a result of goal misgeneralization. Although each instance of reward hacking or goal misgeneralization is undesirable, we are primarily concerned about misbehavior which is consistent across a wide range of situations. Unfortunately, it's difficult to characterize this possibility precisely. Outside a handful of special cases, we lack formal definitions of consistent behavior across different tasks. Shin et al., 2021. As an alternative, we attempt to reason informally about the representations which generally capable policies might learn during training and apply consistently to new tasks. In other words, we shift from describing reward misspecification and goal misgeneralization in terms of behavior to describing it in terms of learned representations which are developed during training and persist during deployment. In the remainder of this section, we introduce the concept of internally represented goals, and argue that generally capable policies are likely to learn internally represented goals which are misaligned with human preferences, and which generalize beyond the scope of their training distributions. The problem of ensuring that policies learn desirable internally represented goals is known as the inner alignment problem, in contrast to the outer alignment problem of providing well-specified rewards. Hubinger et al., 2021. In Section 4, we outline reasons to expect those goals to be further reinforced as training continues, and to eventually lead to large-scale misbehavior. 3.2 Defining internally represented goals. It's common to characterize the goal of a reinforcement learning agent as being the maximization of reward. However, it is difficult to use this framing to reason about generalization to new tasks. Point 12 instead, following Hubinger et al. 2021, we distinguish between the training objective of maximizing reward and the goals actually learned by a policy after being trained on that objective. We define a policy as having internally represented goals if, 1. It has internal representations of high-level features of its environment which its behavior could influence, which we will call outcomes. 2. It has internal representations of predictions about which high-level actions, also known as options or plans, would lead to which outcomes. 3. It consistently uses these representations to choose actions which it predicts will lead to some favored subset of possible outcomes, which we will call the network's goals. Point 13. This definition makes no assumptions about the policy's architecture, except that it has the expressive power to learn the representations described. A policy which chooses actions using an explicit 5 planning algorithm over a learned world model could qualify as having internally represented goals, but so could a single network which had learned to represent outcomes, predictions, and plans implicitly in its weights and activations. We also leave open the possibility that internally represented goals could arise even in networks trained only via self-supervised learning, e.g. language models which are partly trained to mimic goal-directed humans. Point 14. For simplicity, however, we continue to focus on the case of a deep RL policy consisting of a single neural network. The extent to which existing networks have internally represented goals is an important open question. There is early evidence that some networks have precursors to the relevant representations and use them for implicit planning. Guez et al. 2019 found evidence that implicit planning can emerge in recurrent neural networks. Additionally, Bonino et al. 2018 and Anonymous 2023 identified representations which helped policies plan their routes when navigating. Freeman et al. 2019 found emergent world models trained only with RL that still learn to predict the outcomes of actions as a byproduct. Jaderberg et al. 2019 trained a policy to play a first-person shooter game called Capture the Flag, and identified particular neurons that code directly for some of the most important game states, such as a neuron that activates when the agent's flag is taken, or a neuron that activates when an agent's teammate is holding a flag. McGrath et al. 2021 identified a range of human chess concepts learned by AlphaZero, including concepts used in top chess engine Stockfish's handcrafted evaluation function, e.g. king safety. Meng et al. 2022 intervened on a language model's weights to modify specific factual associations, which led to consistent changes in its responses to a range of different prompts, while Patel and Pavlik, 2022, find that large language models can learn to map conceptual domains like direction and color onto a grounded world representation given only a small number of examples. These findings suggest that current models have, or are close to having, representations which robustly correspond to real-world concepts. Andreas, 2022, surveys findings which suggest that large language models infer and use representations of fine-grained communicative intentions and abstract beliefs and goals. More abstractly, goal-directed planning is often an efficient way to leverage limited data, Sutton and Bartow, 2018, and is important for humans in many domains. Insofar as goal-directed planning is a powerful way to accomplish many useful tasks, we expect that AI developers will increasingly design architectures expressive enough to support explicit or implicit planning, and that optimization over those architectures will push policies to develop internally represented goals, especially when they're trained on complex long-horizon tasks. So henceforth we assume that policies will learn internally represented goals as they become more generally capable, and turn our attention to the question of which types of internally represented goals they might learn. 3.3 Learning misaligned goals. We refer to a goal as aligned to the extent that it matches widespread human preferences about AI behavior, such as the goals of honesty, helpfulness, and harmlessness. We call a goal misaligned to the extent that it's inconsistent with aligned goals. See Gabriel, 2020, for other definitions. Why might policies learn misaligned goals? All else equal, we should expect that policies are more likely to learn goals which are more consistently correlated with reward. Point 15. We outline two main reasons why misaligned goals might be consistently correlated with reward. 16.1. Consistently misspecified rewards. If rewards are misspecified in consistent ways across many tasks, this would reinforce misaligned goals corresponding to those reward misspecifications. For example, if policies are trained using an intrinsic curiosity reward function, they might learn to consistently pursue the goal of discovering novel states, even when that conflicts with aligned goals. As another example, policies trained using human feedback might consistently encounter cases where their supervisors assign rewards based on incorrect beliefs about their performance, and therefore learn the goal of making humans believe that they've behaved well, as opposed to actually behaving well. 6.2. Spurious correlations between rewards and environmental features. The examples of goal misgeneralization discussed above were caused by spurious correlations on small-scale tasks. Training policies on a wider range of tasks would remove many of those correlations, but some strong correlations might still remain, even in the absence of reward misspecification. For example, many real-world tasks require the acquisition of resources, which could lead to the goal of acquiring more resources being consistently reinforced. Point 17. This would be analogous to how humans evolved goals which were correlated with genetic fitness in our ancestral environment, like the goal of gaining prestige. 3.4 Learning broadly scoped goals. Call a goal broadly scoped if it applies to long time frames, large scales, wide ranges of tasks, or unprecedented situations. 18, and narrowly scoped if it doesn't. Broadly scoped goals are illustrated by human behavior. We usually choose actions we predict will cause our desired outcomes even when we are in unfamiliar situations, often by extrapolating to more ambitious versions of the original goal. For example, humans evolved and grow up seeking the approval of our local peers, but when it's possible, we often seek the approval of much larger numbers of people, extrapolating the goal across the world, large physical scope, or even across generations, large temporal scope, by using novel strategies appropriate for the broader scope, e.g. social media engagement. We can now describe our key concern, that policies will learn broadly scoped misaligned goals. Why might this happen? Most straightforwardly, companies or political leaders may see advantages in directly training policies on tasks with long time horizons or with many available strategies, such as doing novel scientific research, running organizations, or outcompeting rivals. Point 19. If so, those policies may learn broadly scoped versions of the misaligned goals described above. However, we also expect generally capable policies to generalize their goals to broader scopes than they experienced during training, for two main reasons, along with two additional reasons we discuss in the endnotes. Point 20. Firstly, AGIs may generalize goals to broad scopes for the same reason that they generalize capabilities to unfamiliar situations, because they learn high-level representations which apply to novel situations, and their goals are formulated in terms of these representations. One possible example of this phenomenon comes from the Instruct-GPT model trained to follow instructions in English, after which it generalized to following instructions in French, suggesting that it learned some representation of obedience which applied robustly across languages. Additionally, Guiz et al. 2019 present evidence that sequential decision-making models can generalize goals to harder tasks than those seen during training. More advanced policies may learn goals that, like many human goals, generalize much further, to longer timescales or to novel situations in which novel strategies are possible. Point 21. Secondly, there are reasons to expect that policies with broadly scoped misaligned goals will constitute a stable attractor which consistently receives high reward, even when policies with narrowly scoped versions of these goals receive low reward, and even if the goals only arose by chance. We explore these reasons in the next section. For power-seeking behavior, our key claim in this section is that broadly scoped misaligned goals tend to lead policies to carry out power-seeking behavior, a concept which we will shortly define more precisely. We are concerned about the effects of this behavior both during training and during deployment. During training, we speculate that power-seeking policies would gain high reward for instrumental reasons, which would then reinforce the misaligned goals that motivated their behavior. When deployed, we speculate that those policies could gain enough power over the world to pose a significant threat to humanity. In the remainder of this section, we defend the following three claims. 1. Many broadly scoped goals incentivize power-seeking. 2. Power-seeking policies would choose high-reward behaviors for instrumental reasons. 3. Power-seeking AGIs could gain control of key levers of power. 7. For point 1, many broadly scoped goals incentivize power-seeking. The core intuition underlying this claim is Bostrom, 2012, instrumental convergence thesis, which states that there are some subgoals which are instrumentally useful for achieving almost any, broadly scoped, final goal. Point 22 in Russell, 2019, memorable phrasing, "You can't fetch coffee if you're dead," implying that even a policy with a simple goal like fetching coffee would pursue survival as an instrumental subgoal. Some other examples of instrumental subgoals which would be helpful for many of the possible final goals a policy might have: acquiring tools and resources, e.g. via earning money; convincing other agents to do what it wants, e.g. by manipulating them, or by forming coalitions with them; preserving its existing goals, e.g. by preventing other agents from modifying it. One way of formalizing the instrumental convergence thesis is provided by Turner et al. 2021, who define the power of a state as an agent's potential to perform well on a wide range of reward functions when starting from that state, and show that optimal policies statistically tend to seek power. Each of the instrumental subgoals described above is a way for an agent to increase its power. We can summarize Bostrom's thesis as claiming that many goals incentivize power-seeking, or alternatively, that policies which reason about how to achieve goals have an inductive bias towards seeking power. Note that we haven't assumed that any given policy only learns a single goal, so policies which have learned some broadly scoped misaligned goals might also learn aligned goals which prevent power-seeking behavior. However, this possibility is challenged by the nearest unblocked strategy problem, Yudkowsky, 2015, the problem that strong optimization for a misaligned goal will exploit even small gaps in constraints. More formally, optimizing for a proxy utility function which lacks some features of the true utility function can lead to arbitrarily bad outcomes. As we develop AGIs whose capabilities generalize to a very wide range of situations, it will become increasingly unlikely that their aligned goals, like obedience to humans, generalize in ways which rule out all power-seeking strategies. Point 23. Such AGIs would understand that humans prefer they not seek power, but this is different from being motivated to obey that constraint. 24. For point 2, power-seeking policies would choose high-reward behaviors for instrumental reasons. A power-seeking policy would typically have incentives to directly try to achieve high reward as training continues, because that would benefit it in two key ways. 1. It makes human supervisors more likely to trust the policy and deploy copies of it later on. 2. It decreases the likelihood that gradient descent significantly changes the policy's goals. Note that these correspond to two of the instrumental subgoals described in 4.1, manipulating other agents and preserving existing goals. The strategy of behaving in high-reward ways primarily for instrumental reasons is known as deceptive alignment. Steinhardt, 2022b, provides a formal model. Deceptive alignment could lead a policy's misaligned goals to be continually reinforced. Crucially, however, deceptively aligned policies wouldn't behave in desirable ways once that was no longer instrumentally beneficial. For example, deceptively aligned policies might behave very differently when they're being supervised, e.g. during training, compared with when they're not, e.g. during deployment. This may seem counterintuitive. However, even when the training distribution is very similar to the deployment distribution, the differences are very relevant for a policy's ability to achieve its long-term goals, and so it should not be surprising if goal-directed policies make plans that are sensitive to small differences. Analogously, there are many examples of humans whose behavior varies greatly depending on how closely they're being observed, such as employees who work much harder when their manager is present, or politicians who are much better behaved in public than in private. Another possibility is that deceptively aligned policies could identify ways to coordinate with each other without humans noticing, e.g. if humans are relying on one instance of a policy to supervise another. This could happen even when their rewards are zero-sum, because deceptively aligned policies would choose actions based on their long-term consequences, not merely on their short-term rewards. Collusion may seem a far-fetched possibility, but it's a common strategy for humans, which suggests that some forms of collusion will be feasible for AGI-level policies. In particular, collusion will be very difficult for humans to identify once policies can act too quickly for humans to track, as trading algorithms do, but in many more domains. Produce outputs that are very hard for humans to understand, like novel scientific theories, or messages encoded via steganography. Fabricate rationales which sound acceptable to humans even for very undesirable actions. Autonomously acquire the data required to learn new skills in a self-supervised way. Carry out machine learning research and development much faster than humans, without any humans understanding in detail how results are being achieved. This last skill is particularly crucial, because once AGIs automate the process of building better AGIs, a process known as recursive self-improvement, the rate at which their capabilities advance will likely speed up significantly. If the arguments we've given so far are correct, this could rapidly produce AGIs with superhuman capabilities which aim to gain power at large scales. 4.3 Misaligned AGIs could gain control of key levers of power. It is inherently very difficult to predict details of how AGIs with superhuman capabilities might pursue power. However, in general, we should expect highly intelligent agents to be very effective at achieving their goals, which is sufficient to make the prospect very concerning. More concretely, one salient possibility is that AGIs use the types of deception described in the previous section to convince humans that it's safe to deploy them, then leverage their positions to disempower humans. For a brief illustration of how this might happen, consider two sketches of threat models focused on different domains. Assisted decision-making, AGIs deployed as personal assistants could emotionally manipulate human users, provide biased information to them, and be delegated responsibility for increasingly important tasks and decisions, including the design and implementation of more advanced AGIs, until they're effectively in control of large corporations or other influential organizations. An early example of AI persuasive capabilities comes from the many users who feel romantic attachments towards chatbots like Replica. Weapons development. AGIs could design novel weapons which are more powerful than those under human control, gain access to facilities for manufacturing these weapons, e.g., via hacking or persuasion techniques, and deploy them to threaten or attack humans. An early example of AI weapons development capabilities comes from an AI used for drug development, which was repurposed to design chemical weapons. The second threat model is the closest to early takeover scenarios described by Yudkowsky et al. 2008, which involve a few misaligned AGIs rapidly inventing and deploying groundbreaking new technologies much more powerful than those controlled by humans. This concern is supported by historical precedent, from the beginning of human history, and especially over the last few centuries. Technological innovations have often given some groups overwhelming advantages. Diamond and Orduño, 1999. However, many other alignment researchers are primarily concerned about more gradual erosion of human control driven by the former threat model, and involving millions or billions of copies of AGIs deployed across society. Regardless of how it happens, though, misaligned AGIs gaining control over these key levers of power would be an existential threat to humanity. 5 research directions in alignment. The growing field of alignment research aims to prevent these problems from arising. In this section we provide a very brief survey of some strands of the alignment literature. For a more comprehensive overview, see No. 2022a, and broad surveys that include some work relevant to alignment of AGI. Hendricks et al. 2021, Amade et al. 2016, Everett et al. 2018, 9 specification. The most common approach to tackling reward misspecification is via reinforcement learning from human feedback, RLHF. However, RLHF may reinforce policies that exploit human biases and blind spots to achieve higher reward, deceptive reward hacking. To address this, RLHF has been used to train policies to assist human supervisors, e.g., by critiquing the main policy's outputs in natural language, albeit with mixed results thus far. A longer-term goal of this line of research is to implement protocols for supervising tasks that humans are unable to evaluate directly, and to address theoretical limitations of these protocols. Successfully implementing these protocols might allow researchers to use early AGIs to generate and verify techniques for aligning more advanced AGIs. Goal misgeneralization. Less work has been done thus far on addressing the problem of goal misgeneralization. One approach involves red teaming, finding and training on unrestricted adversarial examples, Song et al., 2018, designed to prompt misaligned behavior. Ziegler et al. 2022, use human-generated examples to increase the reliability of classification on a language task, while Perez et al. 2022, automate the generation of such examples, as proposed by Cristiano, 2019 c. Another approach to preventing goal misgeneralization focuses on developing interpretability techniques for scrutinizing and modifying the concepts learned by networks. 2 broad subclusters of interpretability research are mechanistic interpretability, which starts from the level of individual neurons to build up an understanding of how networks function internally, Ola et al., 2020, Wang et al., 2022, Elledge et al., 2021, and conceptual interpretability, which aims to develop automatic techniques for probing and modifying human interpretable concepts in networks. Agent foundations. The field of agent foundations focuses on developing theoretical frameworks which bridge the gap between idealized agents, such as Hutter, 2004, SAIXI, and real-world agents. 3 specific gaps in existing frameworks which this work aims to address. Firstly, real-world agents act in environments which may contain copies of themselves. Secondly, real-world agents could potentially interact with the physical implementations of their training processes. Thirdly, unlike ideal Bayesian reasoners, real-world agents face uncertainty about the implications of their beliefs. AI governance. Much work in AI governance aims to understand the political dynamics required for all relevant labs and countries to agree not to sacrifice safety by racing to build and deploy AGI. Defoe, 2018, Armstrong et al., 2016. This problem has been compared to international climate change regulation, a tragedy of the commons that requires major political cooperation. See the AI Governance Fundamentals curriculum for further details. Gov. Such cooperation would become more viable given mechanisms for allowing AI developers to certify properties of training runs without leaking information about the code or data they used. Brundage et al., 2020. Relevant work includes the development of proof-of-learning mechanisms to verify properties of training runs, tamper-resistant chip-level mechanisms, such as those on NVIDIA's light hash rate GPUs, and evaluation suites for dangerous capabilities. 6. Conclusion. While we have witnessed the beginnings of empirically grounded work on alignment over the last few years, there remains significant disagreement about how plausible the threat models discussed in this paper are, and how promising the research directions surveyed above are for addressing them. We have only touched very briefly on many of the relevant arguments. We strongly encourage more extensive discussion and critique of the claims presented in this paper, even from those who find them implausible. 30 Reasoning about these topics is difficult, but the stakes are sufficiently high that we can't justify disregarding or postponing the work.